So thanks for joining me for this session. Can everyone see me if I stand here, or is it better if I stand here? Here. Thanks. So thanks for joining for this session. So this session is going to be a bit different. It's not heavy coding. It's designed to give you a different way of thinking about how we design cloud-native applications. So applications that are really there to thrive in the cloud and not just survive in the cloud. So my name is Jansen. I'm a developer advocate at IBM. Get it? And I work as a developer advocate, so I do a lot of presentations like this. I run demos, tutorials, workshops, that kind of thing, around cloud-native technologies, but also things like Java, reactive, and all that good stuff. Now, the interesting thing about me is I didn't come from a technical background. This is me wishing my dad a happy Father's Day from the Bahamas on my field trip. I specialized in a biology degree in fish, which has really not come in very useful in my career, not going to lie. So I switched from a biology degree to a technical career when I joined IBM about 4 years ago, and I jumped straight into the world of Java. So I like to try and bring in my biology background into my technical background and try and come up with different ways of explaining sort of conceptual concepts that often can be hard to understand, hard to remember, or just easier because you can relate it to biology. So, as I said, developer advocate, I'm sort of a software engineer now at IBM, and I like to bring in that biology side. So, this session is relating anatomy and the human body into cloud native. So, what do I mean by anatomy? Well, anatomy here, I've got a definition. So it's really about the branch of science that's concerned with sort of bodily structures of the humans or animals or any living creature, really. And it's about really studying them to understand how they work together as a system. So how does this all relate into cloud? Why do we care about anatomy? And what can we learn from the millennia that nature has had to evolve our bodies into this really effective functioning system? So let's take a look at the evolution to the cloud that we've come on, this journey we've already taken, and why that means that we can now utilize perhaps outside sources like evolution, nature, biology, for inspiration when we're designing the next evolution of our cloud-native applications. So our modern infrastructure has made significant changes, right? We used to run we used to have large applications, and we were using single cores, whereas now we can use multiple cores, we can use virtualization technologies, containerization technologies, we can be running within data centers rather than on-premise. So we've had this underlying infrastructure evolution that has meant we've been able to evolve our apps to improve. So we've been able to evolve our apps from this more modular, monolithic application into, say, microservices, or if you're not using microservices, maybe macroservices or functions. So we've been able to break down our application, and this has been great for our evolution. It means we're now able to isolate bugs independently without bringing down our entire systems. We can update one particular service without having to take down our application and rebuild it entirely. And we're able to add functionality without needing to completely rebuild the entire application. So this has all been great so far, and it's been a fantastic leap forward in this cloud-native evolution. But where do we go from here? How do we improve it? In terms of when it comes to, say, transforming a more modular application into a more microservice-based or distributed application, what technologies should we use individually in our applications? And what steps do we need to be thinking about when we're making that journey? So why are we excited about the cloud? Has anyone seen Toy Story? Please tell me you have. Okay, so we're excited about the cloud, right? Ooh, the cloud. Because the cloud brings with it many benefits, right? We're gaining benefits like cost reduction. The fact that we're now able to essentially outsource the cloud infrastructure that we're running our applications on means that we should be able to benefit from cost reductions. So we're all utilizing joint platforms, which means that those cloud providers are able to have sort of economies of scale. So if they're doing it for lots of people, they should then be able to do it at a cheaper price for you individually because they're able to do it at scale. So we're able to gain cost. We're also able to gain things like scalability. So the fact that we're able to dynamically scale the resources within our applications up and down is a great advantage. It means we're able to dynamically respond to load changes to our applications as and when we need it, while still being able to be cost effective. Whereas before, we might have had to buy resources for the sort of biggest amount of load our application might have come across, and then half the time it's not even being used. Whereas now what we can do is literally just use what we need. So if we need less, reduce the number of resources. If we need more, dynamically increase them. So it's that scalability. And that adds into that resiliency. The cloud gives us resiliency because if we have an increase in load, it's not the same amount of resources trying to deal with that increase. We're now able to increase up the resources, which means we're giving a better service to our customers, and we're less likely to get a bottleneck or a potential failure point or contention point within our system. So we gain this resiliency as well. Fashion. Now, you might not think of fashion as an advantage of the cloud, but actually, when you think about it, our industry is kind of a fashion industry. We follow trends, we get excited about new features and products and facilities. And actually, what the cloud offers is it offers us that capability to utilize the innovation going on to be fashionable, to be giving our customers the latest innovation and the greatest customer service they could get from our applications. So these are the benefits that cloud offer, and that's why we want to be building applications that really thrive within this environment instead of just surviving in it. So what does it mean to be cloud native? Now, I took a look at a bunch of different vendors online and a bunch of different definitions that they provided. A lot of them have very specific terminology, whether that's the type of application you build, like the application architecture you use, or whether that's the technologies and the stack you're using underneath it. Actually, one of the most broadest ones I came across was by the CNCF, and as their name suggests, they're kind of experts in all things cloud native. So if you've not come across the CNCF before, it's the Cloud Native Computing Foundation, so it's literally in their name. So their definition talks about the fact that cloud-native technologies should empower organizations to build and run scalable applications in modern dynamic environments, whether that be public, private, or hybrid clouds. So it's all about utilizing this technology, whether that's containers, service meshes, microservices. Now, the important thing in this definition is that it doesn't necessarily have to be those things. They do exemplify the cloud-native sort of definition, but you can use a wide variety of tools, architectures, and technologies to achieve a great cloud-native application. So it's all about being able to build these loosely coupled systems that are resilient, manageable, and observable. And we'll see those key words and those key behaviors coming back into it when we look at biology. So what do you need to consider to become cloud native? The first thing you need to consider is, what are you creating? Now, in biology, we have a huge spectrum of different organizations. If you look at an amoeba, for example, that's a single cellular organization. That's a hard word to say. And it basically means that, unlike us, they have a single cell, and instead of having like a dedicated eating system, etc., hunting for food, they literally just absorb it into themselves. So they're so small that they can just absorb in the nutrients they need, and that is what fuels them. So for an amoeba, it's quite a simple system, quite a basic system, and they don't really need that many resources. And because it's a single cell, they don't need specialized cells within them because they can just do everything within that one cell. However, if you start working your way up the evolutionary sort of pyramid, you start getting to more complex organisms. So the next one up is sort of like a worm-type creature. Now, I studied a whole module on this. There's a lot of worms out there in this world. And in this sense, it's sort of about, they start to have specialized cells. They start to have particular cells for particular purposes, but it's still a fairly simple organization. It doesn't have a huge brain or anything. It sort of just exists. And then you start working your way all the way up, and you get to things like chimps, dolphins, humans. You're getting to much more complex organisms. We have specialized cells that do dedicated jobs within us, and we have a brain that is able to process vast amounts of data and information. This is way more complicated than that simple amoeba. So it depends on what you're creating as to which tools and which architectures you need to be putting into place in your own applications. Are you making the version of a human in your application? Is it massively complex, lots of different working parts together, all coming together in conjunction? Or is it a little bit simpler? Maybe you've got less services. Maybe you don't need to have particular architectures or tools because you have a smaller application serving less people. So the first question to ask is, what are you creating? So what's going to be right for your application? Because there's no one answer. It's completely dependent on what you're trying to build. When it comes to thinking about what you're building, the first step is sort of thinking about, okay, what type of application am I building and what architecture is going to be best suited for that particular application? There are lots of different architecture types you can use. We like to call it a spectrum because you might not fit necessarily into one of these boxes, but there are different types. So we've got monolithic, macroservices, microservices, and functions on my slide here. You might not have come across the word macroservices before. It's basically just a larger microservice. So if you, for example, have multiple services that all depend on each other and can't necessarily be completely loosely coupled, then it might be worth making them one larger macro service. And that way you can then have a bounded context around those multiple services so you can enable that resiliency within your application because you don't have microservices dependent on each other. So you've got sort of more finer grained, I guess, on your right-hand side and more coarser grained on the left. Now, the interesting part about this is it actually shouldn't matter about which application choice you use in terms of it being cloud native, because cloud native is just using the best technologies you can to enable you to have those characteristics of resiliency, observability, maintainability, all of these key behaviors and characteristics. And you can achieve them with any of these architecture types. Now, there are obviously some that lend themselves better than others to the distributed nature of the cloud. So, for example, if you have functions, there is probably no point running functions in your own data center, in your own on-premise site, because you're paying per function, per call to that function in the cloud. So if you're running that in your own provisions, then you're paying yourself for the functions that you're already paying for the infrastructure for. It doesn't really make any sense. So there are obviously architecture types that lend themselves more to that cloud distributed nature, but you can use any of these. It's about picking what's right for your application. And actually, here's a useful slider that I tend to recommend to people when it comes to selecting the architecture that's right for them. You might look at that previous chart and go, well, I don't know what's right for my application. And that's fine. You can use tools like this to be able to picture where your organization and your application fit within that scale, within that sort of slider. So I've just put some different factors that can influence the type of architecture you might want to use. Now, the interesting thing about the factors that I've chosen is they're not all specific to the application. Not only does it depend on the application, but it also depends on your organization. If you're not set up to deliver releases to your application more frequently than once a year, then why are you looking at microservices? Maybe you should be considering a monolith or macroservices, because microservices really need really frequent releases, for example. So it's not just about your code, it's also about how you're set up as an organization, what funding you have available, for example, what resources you have available in terms of the people working on this application. So I would recommend, if you're thinking about potentially moving the type of architecture your application is on or building a new application, think about creating a slider system like this with the factors that are most important to your application and working out where you fall on this scale. Coming back to the biology. So now that we've thought about, okay, we've got the type of architecture we want to use, now how do we actually go about building this application to be cloud native? Now, one of the main parts about the body is that we don't just have a mass of material sort of floating around everywhere inside. We have containerization. So our cells containerize the different elements that we need to sustain ourselves. So within the cell, we have the instructions for what that cell needs to do, and that's within our DNA. So if it's a skin cell, it's got the skin cell-specific DNA, and if it's something else, it's got something else. It's also got everything we need to provide energy to that cell. So everything that we need is really neatly packaged within this container of a cell wall, essentially. What that means is that it's really easy to move it, it's really easy to replicate it, and it's really easy to fix it. So if we need, for example, a white blood cell, they're the ones that protect us from infection, so kind of relevant with COVID at the moment. So if we need a white blood cell moved around the body, we can easily do that because it's really neatly packaged. If we need to replicate a cell, so let's say I've been working out at the gym, I need some more muscle, right? I can easily replicate the muscle cells and produce more muscle cells to be able to deal with that increase in load on my system. And I can easily replace and fix them. And this is why this is sort of related to cancerous cells. If our body recognizes that one of our cells has gone wrong, it's not healthy anymore, it should, in a healthy body, be able to get rid of that and replace it with a cell that does work and is healthy. And this is all things that we want to be replicating within our cloud-native applications. We want to be able to easily move them about if we need to change data center, for example. We want to be able to easily replace them in case they go wrong. Let's say one of our containers becomes unhealthy, or one part of our application becomes unhealthy. We want to be able to replace it with a healthy version. So all of these behaviors and characteristics we want to replicate within our application. And a lot of you probably already use containerization already in your own applications, but tools that you can use include things like Docker, and you get the advantages over, say, like hypervisor-based virtualization in terms of not needing to have this guest OS. It's smaller in terms of memory footprint, and you can move it between different cloud environments, so it makes it a lot more flexible in that regard. So in this step, we've already taken a step towards what nature has already shown us. We've already started to containerize. What about deployment, scaling, and management within the body? So now that we've got our container and we've neatly packaged up that section of our application, how do we know how to deploy it, how to scale it, and how to manage it? Well, in the body, our body already naturally does this. So for example, if I have a cut or a scrape, my body knows that that's a danger to my body. It knows that an infection could potentially get in, and it needs to close that up and deal with that immediately. So that's an increased load on my body, and it needs to respond. And so what the body does is it actually deploys specific types of cells, like, for example, platelets and red blood cells and different types of like proteins, for example, to be able to create a clot that then stops that from being an open cut. And that immediately negates the risk of me being infected. So in that sense, it's able to dynamically deploy different types of cells to deal with particular load. It's also able to scale them. So as I said, if I need to rapidly scale up my muscles because I've been exercising or working out or whatever, my body can rapidly manage the number of cells that are dedicated to that particular purpose. So it's able to dynamically scale them in that way. And management. So for example, if I get infected with something, let's say it doesn't matter, it doesn't heal up my cut in time, and suddenly I get infected with an infection. My body is able to manage the cells within it. So the red blood cells come along and essentially recognize, oh, this cell's not meant to be here. Identifies it and identifies it to the body as a potential infection. My body then rapidly scales up the number of white blood cells that are dedicated to targeting that infection so that I don't essentially end up in some sort of fever because I can't manage the infection. So it's all about management of the number of particular cells dedicated to particular purposes based on that load to my system. So nature's already amazing and does this. It does it by itself. And this is, again, what we want to be replicating within our applications. And again, many of you probably already do this. So we can use tools like Kubernetes, for example, to be able to manage the scalability, the management, and the deployment of any containers we need for our application. So if we need more of one particular service, for example, we should be able to dynamically spin up more container instances of that particular service to be able to deal with that load, just like we would if we had a cut or a scrape or an infection. So we can, again, learn from biology in terms of, right, first step, choose what type of application you're making. Choose what type of organization you're making, essentially. Second step, looking at containerization. So just like the cells, containerizing those aspects of our application. Third step, managing that, being able to dynamically scale up and down. What about communication? So we've already talked about the fact that we're able to dynamically manage it, but now we've got these sort of random cells floating about that can't really communicate together. How does our body deal with that? The body has two ways of communicating. You've got the chemical and the electrical signals. So the chemical signals are essentially the way in which the body signals to other cells that something might be wrong or it needs to potentially act on something. So in that sense, you can have essentially hormones flooding through the body that can trigger particular responses. And that's a way of a cell communicating with another cell, for example. And then you've also got the electrical signals. So the electrical signals are essentially our nervous system. So that's the way in which the brain, so the central processing system, can trigger particular actions or particular cells. So we have a really efficient method of communication. One is very long-lasting, but takes a longer period of time, and the other is extremely quick, but doesn't last as long. So we've basically got both covered, and we're able to really effectively communicate cell to cell and cell to the central system. And within our cloud-native applications, we want to be as effective as this. We want to respond to events as quickly as possible. Our nervous system allows us to respond, as I said, really, really quickly. So if I start to pick up a hot pan, and that's obviously a danger to my body, my nervous system will automatically tell me to drop it. It's extremely rapid at responding to events. And we want the same thing within our applications. So we can use things like asynchronous forms of communication, like event-driven architecture, to be able to have that really responsive underlying communication layer within our applications. So it's really important that when you're thinking about, okay, how do the different components of my application communicate, that you're thinking about that asynchronicity and those really fast, rapid response times, because that's how we're able to create applications that really thrive. What about data storage? Data storage is an interesting one within the body because we kind of have both stateless and stateful. You might not necessarily know about one of these methods. So the most obvious one is obviously the brain, huge store of information where we control most of what happens within the body. So this is a fantastic place in which we store, process, analyze, and respond to particular information, data, etc. And this is essentially what controls most of the human body and most of the actions that we take. Now, the one you might not know about, maybe you do, someone in here probably is a PhD in cells, and I'm giving them like a 101 in this, sorry. So you might not know about this one, but some of our cells have inbuilt memory. So you might think of a cell as like a really stupid thing, can't think for itself, just gets told what to do by the brain or by hormones. But actually, we have some really clever B cells. Now, a B cell is one of the cells that's involved in your immunoresponse, so defending the body against infections and things like that. The great thing about the B cell is that we can make something called a memory B cell. So this is essentially the premise of vaccinations, which everyone should be familiar with at the moment. So in here, basically what happens is if you've been infected by something before, let's say coronavirus, and so you've had that through a vaccination in this case, your body then essentially learns to identify the type of cell and what it looks like. Once it knows what it looks like, either from that vaccination or from being infected by it before, it can then create a memory cell. And what this memory cell does is remember the particular flags that that cell has to identify itself. And then that means that next time you're infected with it, hopefully not, but next time you then are able to respond much faster to that infection and hopefully not be as ill and not have as many symptoms. That means that we have a much greater advantage if we ever get reinfected with the same thing. That's why generally if you've had a cold, for example, and your friends get a cold in the same year and maybe you interact with them, you might not get as bad as symptoms the second time round because your body's made these B memory cells. And it basically means we have a greater advantage in our immune system. So we have a bit of both. We have inbuilt memory in some of our cells that they're able to use to access that information immediately, but we also have our information stored in this central repository. So data storage within your cloud-native app, again, this really depends on the type of application you're building and whether you need that information stored in state or whether you don't. So stateless microservices usually have a separate store of data that they then need to communicate with in order to access that. And then stateful microservices have this inbuilt memory built in. It does mean you get low latency between, say, the business logic and the data, but a lot of the time you might be looking at stateless, again, depending on your application. So that's something to consider. Do you want to build stateful microservices or stateless microservices? If you're interested in finding more about stateful microservices and how you can still build cloud native with stateful, my colleague Mary Grigleski has some awesome videos online that you can check out. If anyone wants those, I can give the link afterwards. Okay, so we've looked at all of these things so far. What about when things go wrong? Now, inevitably, things will go wrong in your application. And so we need to be able to build resilient applications that are able to gracefully deal with this. So what about the body? So when it comes to things going wrong in the body, your body is amazing at monitoring it. So we call this homeostasis. Homeostasis is essentially the state of anything physical and chemical conditions within your body, and they're all maintained within living systems. So we have a particular range for all of these different conditions that we can function within. If you start dropping below that range, you're at risk of death, essentially. So temperature is a key one. Everyone knows about hypothermia. That's when we start to drop below the temperature our body needs to be, and areas of our body start to die off, essentially. So our body is fantastic at being able to regulate the different chemical and physical reactions that are going on within the body and be able to constantly monitor them and act if we need to do anything. So for example, if I'm getting chilly, I might start to shiver, get goosebumps, my hairs might stand up, and all of those actions are essentially trying to negate the fact that I'm too cold. My hair standing on end creates an air bubble around me that helps to create warmth. Shivering helps to warm up my muscles. So all of these actions take place because I've monitored my system, I notice that it's not performing at its sort of optimal level, and I'm able to action things to be able to gracefully deal with that. There are lots of different things that our body regulates, so not just temperature, but also things like water, our water balance, our blood sugar, and also just general health throughout the body. So we need to have as much monitoring in our applications as we do in our bodies. We have a distributed system. I don't always know what's going on inside my stomach or inside my leg. You know, my brain's up here, my organs are down here, and so I need a way in which to monitor them and know to be able to react to them. And so we can do that within our applications with various different toolkits. The fact that we now have distributed nature within our applications, you know, we're sending these microservices out, and unlike when we had them locally running, we were able to just go in, take a look, see what was wrong, and that was it. Now we need to build in that monitoring, that observability, to be able to monitor our applications and know when things are going wrong and know what to do about it. As I said, there's various tools you can use, things like Elastic, Kibana, FluentD, Prometheus, Grafana. These are all monitoring tools that you can utilize, and a lot of them are open source. If you want to go and check them out, then please do. And they can enable you to really know, how's the health of your microservices? Is there an issue in terms of, is there something stuck in processing, or maybe it's unhealthy? And to be able to action things to be able to negate that. So maybe if you've got an unhealthy microservice, throwing up new replications of that particular service to be able to deal with that load. So by having this observability, we can enable that resiliency that I was talking about before. And navigating the complexity. So this is the last analogy, I promise, sorry. So navigating the complexity, this is all about, okay, we have this really complex system with loads of different things going on, lots of different specialized cells. How do we navigate the entire thing? We don't necessarily, if you wanted to target my kidney cell, you wouldn't just go in and speak to my kidney cell. It doesn't work like that. Instead, we have the central nervous system. So we have this fantastic central body in which we use to basically control every aspect of our body. The central nervous system and the periphery nervous system work together. So the central nervous system is essentially your spine and your brain. And then the periphery nervous system is all the other nerves that come from that central nervous system. So all the nerves that go to your hands, your fingers, etc., etc. And they work together to be able to control and action anything. So it's sort of like the central point through which all requests come that then need to be sent to particular areas of our body. So for example, if I see food and I'm hungry, as I usually am, that will then send through the central nervous system and say, okay, I need to walk over there to be able to pick up the food, to be able to eat it. Then I'm going to set up a whole process within my stomach to be able to digest that. So there's this central process through which all these requests come, and it's usually through the CNS, the central nervous system. And we can have something similar within cloud-native applications. Now, depending on the complexity of your application, you may or may not need something like this. But having things like API gateways, or for example, using things like proxies, etc., you can have this sort of central place in which through all requests come that can then be sent out to the various different services. This is important because if, for example, you have a service running and you know the particular URL to be able to hit it, for example, that might change if you change where your application is being run or you change the particular instance of it. So it's important that you have this sort of central place in which through you can route all of the different requests in case anything changes. So again, is that resiliency side of things, but this also helps with load management. So being able to send requests to microservices that are healthy and that can deal with that response, and being able to manage the number of instances of that particular service if you need to increase them. So by using all of these analogies, hopefully what I've shown you is that actually you can utilize the inspiration of nature, so we can look at ourselves and think, oh, well, how would my body respond to that? How would my body respond to failure? How would my body respond to, say, an increase in load? let's say I need to fight an infection, or I need to grow my muscles, or I'm working on my running skills. And we can use that to be able to come up with these behaviors that actually, this is really what being cloud native is all about. It's not necessarily about having a microservice-based application that uses these particular technologies and these particular stacks. It doesn't matter what architecture you use. It doesn't matter what type of technologies you use, or the language you're using, or the stack you're using. It's about having an application that's loosely coupled, that's scalable, that's observable, and these are all the same behaviors that we mimic from biology itself. So all of these behaviors we can learn from and hopefully utilize when we're creating our own cloud-native applications. So how do we actually achieve each of the behaviors that I just showed on that slide there? This is where we get more into the technical side of things. You know, what technologies can we utilize? What methodologies can we utilize? One you're probably all familiar with is the 12-factor app methodology, and this has been extended to the 15-factor app methodology. If you wanted to check that out, there is a free ebook online that you can see. So the 12-factor methodology, if you're not familiar with it, is essentially 12 factors, hence the name, that set out the different things that you should be thinking about when building a cloud-native application. And they actually link really well into the behaviors that I just showed in this previous slide. Now, the reason I like this methodology in particular is because it doesn't have a particular technology or stack or language that it specifies within it. It's very language and platform agnostic, so everyone should be able to pick up and utilize the factors that are within this. So it utilizes a lot of the things that we've been talking about and really enables you to build effective cloud-native applications. There is a 12-factor app workshop, which I can send you a link to if you're interested in trying that out yourselves. Another one that you can utilize, there's loads of these. I've just picked out a couple of methodologies that I think are particularly effective. So this is from the CNCF again, the Cloud Native experts. So they've got this Cloud Native trail map that you essentially go along. And again, it takes you through the various different components that you should be thinking about when you're trying to create an effective Cloud Native application. So thinking about things like your orchestration, like we were talking about before, being able to manage and scale and deploy those various aspects of your application. So it takes you through all of the various components that I've sort of already covered and that our body does automatically. We also have an IBM Garage methodology book. So if you wanted to check this out, this is a great sort of free resource that takes you through various different stages of your modernization journey as you're moving to the cloud and can help you out with making that journey yourself and choosing the particular technologies and methodologies you want to use. If you want to check out anything that I've sort of mentioned in person, like how do I use Grafana, for example, to be able to have monitoring within my application, or maybe more simpler, like how do I create effective reactive applications, we've got some free online labs. I'll be doing a workshop, I think it's at 5 today, in the Coding Cafe, and it's utilizing these labs. So if you guys want to come along to that, you can, and I'll be running through a lot of these things in a hands-on manner. If you don't want to come along because you're bored of the sound of my voice, which is totally fine, you can do it in your own time. The link's here if you wanted to use that. They won't be going away anytime soon, and there's tons of labs that we've got up there. They're all based off the Open Liberty Guide, so if you get bored of the labs we've got on that workshop page, we've got about 37, I think, on this website. So loads for you to get your teeth into around various different cloud-native technologies and tools. So if I haven't given you enough homework already with all the links I've given throughout this presentation, here's some more useful links if you're interested in this topic. So things like an overview of Cloud Native, just in case you wanted that definition to take away and really remind yourself of as you make this journey. How to build a Cloud Native microservices application in Java. So that's a really step-by-step series, which takes you through that modernization journey. So that was a really useful one for me. An overview, how to modernize your valuable Java applications, how to choose the right Java runtime, and also, if anyone wants to see me with a model of a cell, talking about cells even more, because you just loved this so much, then check out the last video, which is about 5 minutes long. Cool. And with that, thank you very much for listening. So I've got some time for questions, if anyone has any, unless I've stunned you all into silence. No, otherwise you just get a really early break time for coffee and all things nice. No questions? Anyone? Literally stunned you all. Yeah.
I was wondering, because you mentioned that you can have a
Yeah, so as I said, my colleague Mary does an entire 1 hour presentation on this where she goes into it in a lot more detail. So I'll get you the link to that. It's online on YouTube, and I can get you a link to that. Stateful services can be cloud native. It's just I think it's a stereotypical, people think cloud native applications have to be microservices, and actually we've come sort of full circle and realized actually there's a whole bunch of architectures I can use, and it's just, I think a lot of the time it's people seeing something really cool, like I said, something fashionable, and thinking, Netflix has done it, and this looks amazing. And we want to copy it, right? I think it's a similar thing where everyone sort of went to stateless microservices. This is not necessarily what you need within your application. So if you want to check out more about how you make that effective in cloud-native applications, I'll send you the link to her talk. She goes into it in a lot more detail. Yeah, no worries. Come see me after. Yeah. Any other questions? Yeah.
I was wondering if you had any experience in robotics, because it's an interesting because I'm not particularly well versed in robotics, but presumably the structure and the way that they have robots, they probably emulate a similar cloud-like structure in their own control structures, right? But yeah.
I like going through my history here. Yeah, I did do robotics, yeah. Not in as much detail as you'd expect. So I didn't go into a robotics company or anything, but that's the way I got into tech. So when I was younger, I was like, I'm going to be like the next David Attenborough. It's going to be great. I'm going to do biology. And then I was like, but I kind of like tech. So then I went into robotics. I ended up in America teaching for three months, kids there with anyone use the Lego Minecraft sets? Yeah. So I was teaching them robotics through that, using the Lego sets. So I did a little bit of it, sort of teaching that, looking into it a bit. We built a robot that was designed to recognize QR codes on boxes and pick them up in a competition. I was using R and stuff, but nothing too complex. But yeah, it's a whole interesting area or field where the two meet, right? Where you've got biology and technical innovations. I mean, there's some insane work going on with prosthetics at the moment in terms of being able to generate prosthetics that can link into the nervous system. It's just fascinating. I'd love to go into it in more detail at some point, but yeah, robotics is a cool area to go into. There was a question over here, yeah.
Do you have any rule of thumb or suggestion about how to set the right granularity of your application?
Yeah, I would say, there's various different techniques you can use, right, to be able to come up with the bounded contexts of which particular areas of your application should be split up and into what granularity level, right? So I would say, for me, generally I find it easier to use things like BDD, so business domain context, so utilizing things like, okay, I've got a restaurant app. So in my restaurant app, I have particular functions that link to particular business functions. So instead of looking at the code itself necessarily and the particular classes that I've created, etc., looking at, okay, what functionality, what business functions do I have from this application? So as a client, what are the functions I'm going to be doing? Well, in a restaurant app, I'm probably going to be booking a table. I'm probably going to be paying, maybe, via the app. I might be looking at the menu. I might be looking at the dietary requirements. So by using it from a sort of a business domain context and looking at that aspect of my application, I generally find that's a good sort of bounded context to then have for that microservice, for example. So I might have a book a service. I might have a payment service. I might have a menu service. And I find that a good way to break them out. In terms of the granularity, I would say, my personal opinion, start larger and work down. A lot of people struggle because they try and create these tiny microservices, and then they end up with loads of microservices, and half of them are dependent on the other, and gets into this huge dependent mess. And you end up with basically a distributed monolith, which is exactly what we're trying not to achieve. So I would say if you start larger, you can always break them down further. And I would use things like BDD to be able to come up with those different contexts. Yeah, I don't know if anyone else had any contradictory advice. I'm not an expert, so it completely depends on your application, but those kind of techniques and methodologies can really help when you're making that journey. Yeah. Cool. Any other questions? No, I've just stunned you all. Cool. I'll let you go to your lunch break early. Thanks very much, guys.